Namaste. Welcome to lecture 1 of week 7. I hope that by now it must be clear to you that nanomaterials have large number of applications, and as we move forward these will find even more number of applications in future. It is also clear by now, hopefully to all of you, that synthesis protocols of these nanomaterials are not very difficult. Meaning you can make nanomaterials easily. It is only that we must have the capacity to tune the physiochemical properties of these targeted nanomaterials as per the need of the end user. Therefore, we must look at different types of features which are required to continuously drive the interest in nanomaterials. One of the most conventional areas where materials have always been used is magnetism, but we have still not discussed anything till now as to what will happen when we take the size to nanometer sized, and then will the magnetic property get modulated or they will remain same. Variation in electrical properties must be clear to you by now, but associated to the motion of electrons we also know is the property of magnetism. So, what happens at nanoscale? Is there a feature or there are features which can lead to the field of nanomagnetism or magnetism at nanoscale? In this week, we will focus on this very interesting and novel topic of magnetism at nanoscale or nanomagnetism. So, what are we going to cover in this lecture? We will talk to you about the basics of magnetism. Then we will discuss the magnetic domains. What are the various types of magnetism, and then we will try to investigate and learn how does nanoscaling modulate the magnetic response in these materials, and that is what we are going to call as nanomagnetism or magnetism at nanoscale. So, if you understand magnetism, it is basically the capacity of particles to either attract or repel. One of the fundamental concepts associated to magnetism is magnetic moments, which is also called as magnetic dipole moment. Dipole, please remember, magnetic monopole does not exist. So, you are always talking about dipole. This magnetic moment is the fundamental vector quantity that provides the strength and orientation of a magnetic field produced by an magnet. So, what will happen? This magnetic moment origin lies in two main sources. One is the electron spin. So, the magnetic moment coming in from the spin of the electron, that is the electron spin magnetic moment, and because these electrons are revolving around the nucleus, you have the orbital magnetic moment. And in terms of magnetic moment, the order parameter magnetization is defined as magnetic moment per unit volume. Magnetization is the consequence of the applied magnetic field, and that is why you call as MH curves. So, magnetization is the order parameter and H is the external stimuli. And how do we define magnetization? It is magnetic moment per unit volume, and therefore, you have this unit as ampere per meter. As we know, magnetization is a measure of material's response to an applied magnetic field. That means, applied means external stimuli. If you look into magnetism, the classical picture is given by, it is as if coming in because of the current carrying loop. So, electron moving around in a loop, that gives you the origin of a spin magnetic moment, and quantum picture tells you it is a combination of both spin as well as orbital magnetic moment. In fact, if you analyze, you find that the magnetic moment due to the spin is equal to the magnetic moment due to the orbital motion in the first Bohr's orbit, and it is expressed as Bohr magnetron mu b. Bohr magnetron thus gives you what? It gives you the magnitude of the magnetic dipole moment of an electron orbiting in an atom with a given angular momentum. So, what do we get? We know from Bohr's model that we can write mvr is equal to nh cut. Magnetic moment of an electron is mu, that is equal to pi r square I, that is equal to E h cut upon 2 m e with a negative sign. Hence, mu b is E h cut upon 2 m e. E is a constant, h cross is a constant, and you have the rest mass of electron which is known. Hence, mu b comes out to be of the order of 10 raised to minus 24 ampere meter square. So, you now know that this is the unit in which the magnetic moment will be scaled up. If you look into the systems, then there can be two types of arrangement. Of what? Of domains which are made up of dipoles. So, you can have a domain which is a combination of many dipoles, but effectively the magnetic field is given in one direction. So, you have a effective magnetic field or magnetization being felt in this domain. So, if the field is 0, applied field is 0, then the net magnetization is also 0, because you find that somewhere this field may get cancelled by a combination of this and this field. So, for every magnetization which is being felt by one domain, there is a cancelling field. But if you have an externally applied field, then magnetization is not 0 and you get a net magnetization in the direction of the applied magnet. This is a typical picture where you see the microcrystalline grains within a piece of hard magnet, NFB magnets. These are hard magnets. So, you can clearly see that there is certain ordering taking place. Based on such arrangements, you classify magnets of various types, and the phenomena of magnetism is then defined as: you can have a paramagnetic state or paramagnetism, where there is random orientation of magnetic moment which can align on application of applied magnetic field, but the moment the field is taken out, again M goes to 0. Then you have ferromagnetism, where magnetic moments are aligned and you get a net magnetization even on removal of the applied field. So, they can be used for permanent magnets. Then comes the class of antiferromagnetism or antiferromagnetic materials, where you have domains with equal and opposite magnetic moments or magnetization. That means, you get net magnetic moment which is 0. And finally, you have ferrimagnetic or ferromagnetism based materials, where you have magnetizations array which are opposite in direction, but their strengths are not the same. Hence, effectively you do get certain magnetization in the direction of the applied field. You have different classes of materials which show such phenomena. Each have their own advantages and limitations. The first measurement which we do to understand the magnetic properties in materials is the determination of its hysteresis loop, which is a graph between B as a function of magnetization, that is applied force H. So, you have flux density and versus magnetizing field. So, when you start, that is M is equal to 0, H is equal to 0. Then slowly all the, even if there are randomly distributed and oriented dipoles, when you apply a field, slowly let us say in this direction, then these domains or dipoles start to align in the direction of applied magnetic field. So, what happens as you increase the magnetizing force, the magnetization increases and you have the increasing trend in the curve. But beyond the certain point, when all the domains or dipoles have aligned in the direction of the applied magnetic field, you will see saturation, that is called saturation magnetization. Now, you reverse the field. Now, I want to remove the field. Ideally, you will find that the magnetization should go back to 0. It does not happen. You see that on removal or on reduction of the magnetizing field, the loop does not trace back the path it was showing in the first cycle. Then at certain point, when H is 0, then also you see certain B value. This is called the retentivity. To make magnetization 0, you have to apply magnetizing force in the opposite direction. So, you see when B is 0, H is actually not 0, it is having a value which is negative with respect to the initial trend which you are seeing. This is called coercivity. Then when you further increase the magnetizing force, you find that the strength of the magnetization increases. It starts showing increasing trend. Again, it reaches saturation and then follows the path, that is, it shows retentivity in the opposite direction also before going to the 0 value for positive H. Please note that if you have an hysteresis loop, then every time we draw this kind of curve, but this part is only seen in the first cycle. Second cycle onwards, this part is not observed. So, if you do the hysteresis loop measurements and very slow hysteresis loop measurements, then only you would see this first part. Otherwise, you will just see in a CRO, you will just see this kind of loop. Reason being, because of the high frequency at which the signal is changing, and hence you do not see it visually, this part in the hysteresis loop. Now, the question comes, this hysteresis loop was being observed in the bulk materials. What happens at nanoscale? Will there be modulation in the magnetization, or the features will remain the same. Will surface to volume changes observed in nanomaterials impact the phenomena of magnetism? Because you are seeing confinement effects in charge movement. Will it impact the magnetic properties? Because we have already seen that the electronic properties do get modulated. What is the impact on the magnetic field? If so, then can dipoles or domains also get impacted by thermal fluctuations? And will there be impacts as we go on changing the dimensionality from bulk to wire to well to dot like structures? So, any three of the types of nano structures which we consider, will there be changes? If you see, then it is observed that what happens, that the coercive field shows modulation. It increases as size decreases from bulk to single domain region. This is called as single domain region or elongated grains. Let us spend some time on understanding what does this concept of elongated grains mean. Now, suppose you have a material where you have confinement in this direction. So, well like structure. There are domains which are, for example, randomly oriented. But because of this dipole-dipole interactions and exchange interactions, this domain or dipole will start impacting the neighboring domain or dipole significantly. Hence, what will happen? One of these, whichever has higher strength, will force the other to align in its direction. So, these two have now aligned in one direction. Now, these two will enforce the third to align in the direction they are pointing, and then you will continue with the phenomena. Hence, what will happen? You will end up with a scenario that although they are separate domains, but they are all pointing in one direction. And how do we define a domain? You have large number of dipoles which are all aligned in one direction and giving you a net magnetization. Here, there are domains which are effectively aligned in one direction. So, it looks like a single domain or it looks like a large grain, because there are multiple grains which are now aligned and giving a net magnetization, and they are all made up of particles having the same chemical formula. So, you cannot differentiate between one grain from the other hence it appears to be an elongated grain. So, single domain regions are also called as elongated grains, and because of this there is an elimination of domain walls, motion and any preferred dominance coming in from the coherent spin rotation, because now all of them you are finding are in one direction. So, what will happen? They are going towards ferromagnetic type structures. Hence, you are going to see an increase in Hc as size decreases. When the size is reduced below the super paramagnetic limit, then there is again a drop in Hc. Why? Because here the role of thermal fluctuations become dominant and that induces randomization. So, you can plot coercivity as a function of particle diameter. You will find that initially it is 0, then it increases and then it goes towards the bulk phenomena which are related. But that is a very critical observation in reduced size system, because contrary to belief that you reduce the size, all the properties would actually be lost. Here you are able to increase the coercive field, that means the strength has actually increased and you are improving the magnetic capabilities of these systems. So, if you look into large grains, what do we know? That magnetic domains form to minimize the magnetostatic energies, and they, because of the domain wall motion, you have lower coercivity. The intermediate grains would have higher coercivity, but very small grains, it is not like that you can just go on reducing the size and there will be a continuous increase in coercivity. If you go to very small sizes, you will lose coercivity, because their thermal fluctuations will start playing critical role. So, if you look into the corresponding hysteresis loops, you will find that if you are in the range of small size particles, let us say up to 10 nanometers, if you are at a very small size, then you actually end up getting some kind of a paramagnetic kind of structures. If you are in the range of, let us say 2 to 10 or 15 nanometers, this is not exact, then you are getting super paramagnetic behavior. If you have the range of 10 to 100 nanometers, you have well defined hysteresis loop. But if you go to very large particles, then you may actually have a different hysteresis loop with a lower area under the curve. So, you can see the nature of hysteresis loop changes from super paramagnetic to a ferromagnetic type with a strong component of paramagnetism in it if you go to very large size, but if you are in an intermediate region, then you see a well defined hysteresis loop with clear coercivity and retentivity along with the saturation. So, it is a very interesting phenomena. So, just by changing the size of the magnetic particle, you can now change the area under the hysteresis loop, that is your storage capability. Earlier it was always thought that by changing the applied field, you will be changing the capacity of a magnetic material to store information, or the opening of the loop would be dependent on the magnetic strength, but here it is shown that now you can actually obtain the same feature by just changing the particle size. Now, if you see the curves and write what is there, the saturation magnetization decreases if you go to very small sizes. This is happening because you will find spin disordering and reduced coordination of surface atoms along with the role of thermal energy. In certain nano structures which are in the range of, let us say, 10 to 100 nanometers, there is a possible growth in MS due to enhanced spin alignment or interface exchange effects which would be simulated in elongated grain type structures. If you now consider remnant magnetization, you will find this increases in single domain region, decreases significantly in superparamagnetic region, and the ratio of MR and MS depends on particle shape, anisotropy, interparticle interactions is a very important inference which we can draw from these 2 points, and often the ratio of MR by MS is approximately 0.5 for a randomly oriented single domain particles. So, if you plot MS and MR as a function of particle size in, let us say, iron oxide nanoparticles, you may have thought that what would be the role of particle size on magnetization, but there is a simple graph here which shows that MS also increases as we are increasing the particle size, and if you then plot MR, then you see that there would be a peak. So, there would be a critical size of the particle where this would give you the maximum value, and on either side of this peak there would be reduction in the MR values. I hope you will be able to correlate with the concepts of elongated grains, and if you increase the size, then you have 2 structures, maybe 2 elongated grains now competing, and then you start seeing more towards a bulk like phenomena. Similarly, you can plot for HC versus particle size, and similar nature has been observed. So, this is towards the elongated structures, elongated grain type structures, the superparamagnetic type regime, and now you have the bulk regime. So, there is a critical radius where HC also maximizes. So, depending upon the end user requirement, now you can clearly define the particle size which needs to be synthesized for iron oxide itself, so that the desired HC, MS and MR values can be obtained, which was not modeled in the classical picture or even in the quantum mechanical picture when we were modeling and explaining the magnetism in materials. So, this is a very interesting phenomena which has opened avenues for large scale application of magnetic materials with different orders of confinement. So, you can have different types of alloys and you can then tune their MS value, their MT values or HC values. You can also tune the superparamagnetic effects in such magnetic alloys by just changing the particle size of these alloys. These are some more of the references which give you even more interesting results about the magnetism at nanoscale, and I would recommend you to go through them to develop even better understanding of the topic, so that you understand that magnetism, which we have been studying till now, can be. So, once you go through the references and today's lecture, you will understand the origin of magnetism, why it will change as you reduce the size of the magnetic particles, and because making nano sized particles are quite easy, hence you can get large number of new and novel magnetic materials which can be used for varied applications in different industries. So, I thank you for attending lecture number 1 for week 7. Thank you.